Alright, let's look at some more examples of geometric series. I would remind you, we have shown that the sum k equals 1 to infinity of a r to the k minus 1 is equal to a over 1 minus r. Now this is just notation here. This is a one way of writing the series. This is the sigma notation, or this is the summation notation. I usually refer to this as the plus dot 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 notation. I don't know what's a better technical term for it, but there it is. Now this is true only if the absolute value of the ratio is less than 1. All right, and IFF is a shorthand for if and only if. All right, anyway, alternatively, if we start the summation at 0 instead of 1, we could also write this as sum n equals 0 to infinity of ar to the n, and that again would give us the same a plus ar squared as that. It's just I've labeled it in a different way, and again only true if the absolute value of the ratio is less than 1. All right, now on the other hand, you might ask the question, and I usually ask this question to my students: how do you decide whether or not a given series is geometric, right? I mean, I've just been looking at them and saying, oh, it's geometric, right? But how do I know that? What's the thought process? Here's a thought process that you can take. If you had a geometric series, right, and you look at the ratio of the n plus 1th and the nth one, then what happens is you're just left with r, which is why I've been calling this the ratio. See, a geometric series is one for which the ratio of the n plus 1th and the nth term is r, no matter which n you're looking at. So that's a characterization of when a series is geometric. It's geometric only if the ratio of any pair of subsequent terms is constant. All right. So, all right. That also gives us a quick check to see whether or not a given series is geometric. If you're in doubt, here's a non-example. All right. Let's see here. So you've got n e to the n over 7 to the n. So I mean, I can tell you from experience that n sticks just like a sore thumb like that. No, if there's an n sitting there, it's not going to be geometric. Now the e to the n over 7 to the n, that's good. That would work out, but that n is going to spoil it for us. Let's see how it happens. So a to the n plus 1, I mean a sub n plus 1 divided by a sub n is this. This is my a sub n, and to divide by, this is my a sub n plus 1. To divide by a sub n is to multiply by its reciprocal. That's a nice trick, right? And then you do some algebra, you get n plus 1 over n, and e over 7. See, that is not constant. Now if we got rid of the n, this would also be gotten rid of, and we just have e over 7, which would be a constant. And so if we could get rid of the n, it would be geometric, but you know, short of the ability to rewrite the problem, we can't do that. Here's another example. So let's see here. So this one, it's not immediately geometric, but if I split it into two sums, again, taking out a logical loan, we'll see if it pays off. I have pi over 6 to the n from that one, and I pulled the 8 out from the plus 1, and I kept the 8 to the minus n to give me 1/8 to the n. And again, distributing the pi, I get pi over 8 to the n. Good news, and I've somehow I've somehow decided that I don't need to write n equals 0 to infinity here, which is not cool. All right, so I do need to write that here. Anyway, so n equals 0 to infinity of that. Looks like it's geometric with ratio pi over 6 and pi over 8. Both of those are less than 1, and positive, so there you go. Geometric series result gives me that this series converges to 6 over 6 minus pi plus 64 over 8 minus pi. All right. And then another example of a different kind of flavor. So here, looking at the sum n equals 2 to infinity of x to the n. So what I decided to do was to show you about how to change the index and notation here. So what I did is I let j equals n minus 2 which means n is equal to j plus 2. Now, let's see here. When n is equal to 2, that means j is equal to 0, right? And so that's x squared times x to the j equals 0 to infinity. So with that in mind, I can identify that my a is x squared, my ratio is x, and provided that the absolute value of x is less than 1, we have that this series of power functions actually converges to this rational function, x squared over 1 minus x. So this is the neat thing. We could even do geometric series for like a variable. X, I'm thinking out of x here really as a variable. And this is getting ahead a bit. We will talk about these much more a little bit later in the course. This is an example of a power series which represents this rational function. Okay, anyway, I've said enough. Next up is the integral test and estimation of series. All right.